Hi, welcome back. Today we'll look at a broader category of curves called plane curves. And I cannot, I don't know. When I was in your shoes, I didn't think anything of this and kind of blew it off, but it's super important for Calc 3. And I would argue also physics. So in physics, you kind of get this, you kind of work more or less with the X and Y portions of some phenomena separately, right? So there's like the kind of a sideways force and then the gravitational force. And when you put those together, it effectively combines to create the movement of a particular object. So, I mean, you work with vectors a lot there. Calc 3 is kind of like, in my opinion, it's basically just calculus for people who go into physics and engineering. But you use parametric equations an awful lot. I cannot overemphasize that, I suppose. So why even bother? It's going to allow you to have an equation for x and then a separate equation for y, and then you could work with those independently. All right. So here is a set of parametric equations, and the t variable there, that new variable, is called the parameter. So usually they use t for time. Okay. Our first kind of goal is to just sketch these things. And you could use a t-table like you did back in pre-algebra, where you would graph equations of lines and you have an x, so you have a y, and you just plot a bunch of points. That works. Okay. And I call that brute force sketching. So looking at problem 1 from the homework, x. So you get a equation for each variable, and over time you'll kind of be able to recognize them a bit more. I mean, they won't make it as as obvious as what we do in the pre-calculus classes with, this is an exponential curve, this is a logarithmic curve, and they kind of pound that into your head. And they won't do that as much here now in the later classes. But for something like this, you should be able to kind of, all right, that's a circle, or versus, okay, this is an equation of a line. But this guy here, believe it or not, in this presentation is the equation of a line. And like I said, we can do a little t-table type scenario. So now instead of just having x and y, you have t, then x, then y. And you could figure out, and usually they use only non-negative t values, because you're not going to have negative values if you're dealing with time, I presume, in our physical world. So yeah, I'm going to plug 0 into the x equation first, you'll get -3, and then plug it into the y equation, and you get 1. And then so on and so forth, right? Let's just do 2 more. Let's not get carried away. Let's put in 1 for t in the first one. 4 minus 3 is 1. And then plug in 1 for t in the second one. You get 3 plus 1 is 4. Finally, let's do 2. So 8 minus 3 is 5. 2 times, it'd be 7. Right? Okay, so let's plot those points in the xy plane. So we're not doing a t xy plane, it's just xy. Going 1, 2, 3, and then 1. Then 1 and 1, 2, 3, 4. And then 7, 1, 2, whoops, 5. I mean, 1, 2, 3, 4, 5, and 7. 1, 2, 3, 4, 6, 7. So it would be up here somewhere. Okay, then I'll connect the dots, and there is my picture. One other thing, though, another kind of advantage of this method is we can indicate a direction of travel. So you can imagine a particle moving around. We want to know it's going from this direction to this other direction, right? So you could be going in one direction or the other. So how do I do that? You just kind of identify the t value. So this is t equals 0, and then it goes to t equals 1. So it's traveling from 0 to 1, so you put a little arrowhead on it to indicate that direction, okay? And that's as easy as it gets. It's really easy. Okay, so that's kind of your first method. That always works. It's probably how our calculators work. I don't know how Desmos does it. I think it's different, right? I looked it up once, and not a lot of people want to talk about how Desmos does its graphing. It's classified or something. I don't care. But yeah, that would be an interesting research project, is to figure out how the heck Desmos is graphing all that stuff. Anyways, let's look at number 2. So x equals t plus 3, and then y equals t squared. So to eliminate the parameter, I'm going to solve for the parameter in one or the other equation. In this case, it's a little easier to work with that first equation and just move the 3 over, so I'd have x minus 3. I can avoid square roots and stuff like that. And then what you do is take that character and plop them into the second equation. You lose information in doing this, right? We're not going to have orientation anymore. But I can at least put it into a form that is more familiar to me. So this is just a parabola shifted over by 3. So originally it's at 0, 0, but then the x minus 3 means go 3 places to the right and draw your parabola there. Right, so it's going to go like this. And then you could get the orientation when all is said and done by just doing some t values. So look at t equals 0 and then 1 to figure it out. Still have to do a table in that case, but you know. So anyways, plug in 0, so that would be 3, and then 0, and then plug in 1, I get 4, and then 1, right? So it's going to start at t equals 0 at the vertex, and then when t is equal to 1, it'll go to the right. So the arrow direction is to the right. And there's no real convention where to draw the arrow. I just put it in between the 2 dots. Okay. All right, so eliminating the parameter. Let's look at another one of these guys. So here I have x equals square root t, and then y equals t minus 4. So the reason why I'm doing this one is that it's implicitly defining the domain for the t values, right? It's not going to say t needs to be greater than or equal to 0, but implicitly we presume that you and your mathematical knowledge would be able to deduce that fact. Okay, so that implies that t needs to be greater than or equal to 0. And that in turn then implies that x will also be forced to be greater than or equal to 0. Okay, because you're not going to get any negative values out of that equation. All right, so I'm going to eliminate the parameter again. I'm going to square both sides of the x, and I get x squared equals t. Let me get rid of blue. So x squared equals t, and then stuff that into the other equation. It'll be y equals t is x squared, so x squared minus 4. Of course, if we graphed x squared minus 4, we would get a both sides of the parabola, but these restrictions that have been implied, we only actually have the right half of that formula, or right half of that picture. So anyways, x squared minus 4, that means it's a parabola shifted down 4 places. There's its vertex. And what I was going on about, technically, yeah, there is this other side, but because of the square root t, we only really get this other half. Okay. Don't put an arrowhead on the thing. No, you want to indicate the orientation. So if you got an arrowhead on it, they may think, well, he means to go in that direction. No. So don't put an arrowhead on the thing. Rather, do a t-table and then, put your arrow on it then. Okay. So t, again, I'll go 0 and then 1. So when t is 0, x is 0, y is negative 3. And then when t is 1, x is 1, and y is, I don't know why I put, what is wrong with my brain? I have to go in for an Alzheimer's test or something, I swear. 0, y equals 0, it's minus 4, people. And then 1 minus 4 is minus 3. Okay, great. So it's 0, negative 4, I'm at the vertex. And then at 1, negative 3. I get my second value, t equals 1. So that is my orientation then, going to upwards and to the right. Okay, so eliminating the parameter. Another way to eliminate the parameter is using trig identities. So I'll just tack this on as another kind of method, using trig identities. And the three identities that I want everybody in the universe to memorize is these: first, the sine squared theta plus cosine squared theta equals 1. And then the tan squared version. And then the cotan squared version. Right? Okay, you can use those characters to, well, first off, build parametric equations, and then secondly, in our case, kind of sketch the parametric equation. So number 4, we have x equals 4 sine, and it takes a bit of practice, all right? This is not something that is at all intuitive. Like you may be looking at this saying, this is crazy. It takes practice. Anything takes practice. So anyways, how am I going to pull this off? Well, I'm going to solve for sine and cosine in either formula, either equation. So sine of 2 theta equals x over 4. And then on the other equation, I'll have cosine of 2 theta equals y over 2. Okay. Then you just substitute that into your trig identities. So one thing to note is on these trig identities, the angle doesn't really, the thing inside of the sine and the cosine, it doesn't really matter. You can have 5 theta. That won't change the integrity of the equation. It'll still be true. Okay. So, sine squared of 2 theta plus cosine squared of 2 theta is still equal to 1. And then you could just do a substitution. So you get x over 4 squared plus y over 2 squared equal to 1. Oh my gosh, and what is that? It's our new kind of picture that we learned in 10.1. It is an ellipse, and we should be able to blow through that and graph it. So the a value is 4, the b value is 2. I don't really care too much about the foci at this point, then. Centered at the origin, 2, 3, 4, 4, 1, 2, 1, 2. There's the picture. So that's 90% of the question. Then you got to get the orientation. Okay, so again, you're probably going to go and do a table. Get 2 points. I'll start at 0. When theta is 0, x is equal to 0. Y will be the 2, and then try like pi over 4. In that case, you'll have x equals 4 sine of pi over 2, which is 4 times 1, which is 4, and then 2 cosine of pi over 2. 2 times pi over 4 is pi over 2, folks. So you get cosine of pi over 2, that's of course 0. 2 times 0 is 0. So I have 0, 2, which is right here, when theta is 0. And then you'll have 4, 0, when theta is pi over 4. And that indicates this clockwise rotation. So put your arrowhead on it. Make sure you do that. You'll need the point. You don't want to do that. Okay. Number 8 is the same spiel, except now we use one of the other formulas. In particular, it's going to be the second one that I'll use. But anyways, you can tell by the type of trig functions that are sitting around your parametric equations. So here I have a secant and a tan. So you're thinking, well, it's going to be that tan squared formula. Okay. Anyways, at first, in order to pull this off, I have to solve for secant and tan. So I get secant theta is equal to x over 2. And then I get tan of theta is equal to y over 9. And then I can do my substitution. So I get y squared all over 81 plus 1 equals x squared over 4. And that's not quite familiar, but if you move the y squared over, you get x squared over 4 minus y squared over 81. And lo and behold, that's hyperbola, right? So the a value is 2, the b value is 9, centered at 0, 0. The branches are on the horizontal axis. So anyways, 1, 2, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. 6, 7, 8, 9. I'll do my box. So here's my box. I'm not going to worry about foci or anything. I'm just going to get my box, isotopes, and then my branches are on the x-axis. Oops, and it should go through the vertex there. Okay. Again, don't put little arrowheads on your graph because you need to indicate orientation. Right? And that adds to more trouble, right? Because in order to graph this, you're kind of jumping. There's going to be a point where you're not allowed to insert theta values, right? Think about what secant is. Secant is really just 1 all over cosine. So if theta ever causes cosine to be 0, you're going to have an issue with your parametric equation. It just won't work there. It's kind of like an asymptote. So at some point, that asymptote is going to jump from one branch to the other branch. Okay, and so to get the orientation, you're not going to be able to just do 2 values. You actually have to do 4 values in these cases. So anyway, and you have to be careful about which values you pick, right? Because if you pick 2 values and one is on one branch and then you jump to the other branch, it's not clear how you would naturally traverse the picture, right? So anyways, I try to pick my values so that they don't jump that asymptote. So for cosine, you know it's going to equal 0 at pi over 2. So you don't want to use 0 and then pi over 2. Okay, so you see how knowing trig kind of helps here? Knowing your reference angles and all that stuff, having it automatic and having memorized it, okay? It's very helpful. So in my opinion, you're going to have to memorize something. It's like learning a language. You know, can you imagine? I gotta look up every word. I don't know. Maybe with a cell phone, you don't have to learn a language anymore. You just talking to my cell phone. You know, I don't know. Anyways, at 0, it's 2 times secant of 0 is 1. So it's just 2, and then tan of 0 is 0, so this will be 0. So my first point, let me put my points in blue. No, not blue. I'm already using blue. I'll put it in yellow. Okay, so there's my first point. And then pi over 4. Secant of pi over 4 is going to be root 2, so this will be 2 root 2. And then tan of pi over 4 is just 1, so this would be 9. So I go 2 root 2 and then up 9. It seems like I'm probably way up here, or maybe not that far up, because I did have 9 tick marks on my axis. So probably about right there. And that tells me the orientation is going up on that branch. Okay. Then you got to do the other branch. Okay. That's not normally going to follow that you're going to be going down on the other branch. You probably wouldn't have known that if you had not done the experiment, this table. So anyways, plugging in pi. So plug in pi. Secant of pi is -1, so this will be -2. So now I know I'm on the other branch, right? And then tan of pi is, well, cosine, so sine over cosine, sine of pi is 0. That has to be 0. Okay, -2, 0. I'll put a dot there. And then 5 pi over 4. Where the heck is 5 pi over 4, right? 1, 2, 3, 4. It's in the third quadrant. And secant of 5 pi over 4, cosine is going to be negative in that quadrant. So this would be then -2 root 2. So good, I'm on the other branch still. And then tan of 5 pi over 4 in the third quadrant, that's going to be positive. So it's just going to be a 1. Tan of 5 pi over 4 is 1, and then times 9 is 9. So again, the orientation on the other branch is going upwards, like that. Okay. Okay. So they try to at least give you some general formulas for this phenomena, and some of the exercises in the homework. It's very helpful in my opinion, because like I said, these parametric equations are not going to be going away anytime soon in your foreseeable future. These things will crop up in Calc 3 all over the place, so you need to deal with them. Anyways, if you're given this form, right, this H, in our forms number 8 and number 9, the H and the K values are both zeros. So those formulas are pretty simple. But if you see it maybe shifted over, that's still going to be, in this case, a hyperbola. And you could see that by here solving for x. So I get x minus h all over a equals secant. The other guy, y minus k all over b equals tan. And then your formula, tan squared plus 1 is secant squared. Substitute, and you see, or at least you're starting to see, it's some sort of conic section. Oops, I put the terms in the wrong order. Crap. Sorry. Math meltdown. Y minus k, there we go, all over b, and then this thing is all going to be squared. And then on the other side, x minus h all over a squared. Some classes, they get really crazy with it, and they start forcing you to, draw it with the other orientations. And usually it just comes down to maybe replacing theta with negative theta. Will accomplish what you're after. We don't get too carried away with it in any of the stuff I do. Not even in Calc 3. Maybe once in a while you'll want to create a curve that has one orientation versus the other, just to experimentally see kind of what's happening to your scenario. So b squared equals 1. So this is clearly then, again, it's a hyperbola. So anyways, let's look at another problem. So number 14. Now the case is they're going to give you some information. They want you to generate one of these parametric equations. So you're basically back engineering at this point to get your experience on how to perform this. So it's a hyperbola they want. And they're going to want your vertices to be at plus or minus 12, 0. And then they're going to want your foci to be at plus or minus 13, 0. Okay. The fact that second coordinate is 0, that kind of tells you where your vertex is going to be, right? Your vertex is going to be at 0, 0. Then what else is this telling you? Well, if you go back to 10.1 and look up all the variables, the vertex variable tells you the a value. The focus variable tells you the c value. And then from our formulas for a, b, and c, we have that square root formula, basically c equal the square root of a squared plus b squared. We could use that formula to get your b value. Okay, so when all is said and done, it'll be b equals the square root of c squared minus a squared. And so what is that? B equals square root of 169 minus 144. Oh, that one's nice. Is that square root of 25? Oh, that's nice of them. So anyways, then you could kind of either back engineer your formula from your knowledge of trigonometry. So anyways, the formula is going to be x, so x squared all over 12 squared minus y squared all over 5 squared equals 1. And then you could rewrite that as x squared all over 12 squared equals 1 plus y squared all over 5 squared, and then try to line it up with your identities. So our identity is, in this case, kind of scrambled a bit, but it'd be tan squared equals 1 plus secant squared, or it's the other way around, right? It's secant squared equals 1 plus tan squared. 1 plus tan squared. So I'm literally just back engineering. I kind of remember, I've done it enough that I remember how it works in the other direction, so now I can just do it this way. So then we say secant must be x over 12, and then tan must be y over 5. And so our parametric equations, x equals 12 secant theta, and then y equals 5 tan theta. Okay. So no big deal. I mean, you can literally just use these equations, but I mean, the probability of you memorizing this, given all of the other nonsense you have to memorize, is kind of small. So in my opinion, it's more valuable to just do the kind of going back and forth, doing back engineering and stuff. Anyways, let's look at, these things are not unique, right? There's more than one way to get the same graph using different equations. These are not unique. For example, in this case, if you were to kind of eliminate the parameter right here, so I'm going to say, 4t equals, working with the first equation for x, 4t equals x plus 3, and then t equals x plus 3 over 4. I can dump that into my y equation. I get y equals 3 times, oh great, I'm going to have to deal with fractions. I hate fractions. But anyways, y is 3x all over 4 plus 9 fourths plus 1, which I think is 13 fourths. You can use all kinds of other ways to do your parametric equations. You could say, literally just say, well, x equal t, and that y equal 3t all over 4 plus 13 fourths, right? Those are the same line. It's just they've been kind of the position of the dot, so to speak, when you would graph it, would be different. The t equals 0 position would be farther along the curve, right? It'd be in the first quadrant as opposed to the second quadrant with the original way they drew it up. So long story short, there's more than one way to kind of skin a cat. And for your purposes later on, you're going to be dumping these things into integrals, believe it or not. And it's in your benefit, it's in your interest to always start your parameter value at 0. Because when you integrate, then you can go from 0 to whatever, and you hopefully you've done enough integrals to know that if you have a definite integral like this, 0 to the 5 of 3 t plus 1, that thing is going to be a lot easier to integrate than going from 1/3 to 5/7. So you want to avoid kind of these funny ranges for your parameters. And okay, so how is that reflected in my homework? Number 15. We're going to give you an equation of a line and want you to find two parametric equations for it. There's a lot of ways to approach these problems. When I was in your shoes, I would just literally kind of fake it, right? Fake it till I make it. I didn't have any kind of programmatic methodology, and I think in life I've kind of worked towards that, but it's kind of backfired because now I'm basically just programming computers to do my work. So anyways, let's do the easy method first. So the easy method is just to replace x in the equation with a t, right? So let x equal t, and then y will equal 6t minus 5. That will work. You could always do that, and it's not going to be a bad thing, especially if you have something really, really complicated that you need to parameterize. On the other hand, though, sometimes you want to start at a position like let's make sure that I want to start at position 0, -5 when t is equal to 0, and then let's say I want t equals 1. I want the position to be at 1, 1. Okay, so these are in x's and y's. If you look at the first set of parametric equations, it does not fulfill this desire here. Okay, so when t is 0, I get it. Yeah, I get 0, -5. But when t equals 1, I am not getting that. Right. So I'm not. Let's say I want actually x equals 2, and then y to equal 12 minus 5 is 7. Right. Okay, so definitely don't get that from the first set. When t is equal to 1. Let's just make sure, right? So x is equal to, when t is equal to 0, x is equal to 1, y is equal to 1. When t is equal to 1, I get x equals 1, and then y equals 1. That can't be right. This is 0, sorry, 0, and then -5. Jeez, oh man, having, I don't know what's wrong with me. There it is. So, okay, so when t is 1, I get 1, comma, 6 minus 5 is 1. Okay. But I want now this other thingamajig here. Okay, so I think we're all on the same page now. Well, one way you could probably accomplish this is just say that the t values are going from, well, no. But let's do the brute, it's kind of a brute force method, all right? So I'm going to create an equation for x and then an equation for y such that for x, I want the t value to start at 0. So you'll have like a t and then an x, right? So I want the t value to be 0 and then the x value to be 0. And then I want it to go to 2. And then I want the x value, 1. And then I want the x value to be 2. So when t is 1, I want x to be 2. Okay? And then you can get kind of a slope for the x equation. So it would be 2 minus 0 over 1 minus 0, which is 2. And then you got y minus 0 equals 2 times x minus 0. So it looks like y equals 2x. Or in this case, of course, we have different variables, right? So it's x and t. So x is equal to 2t. Right? So here, x is equal to 2t. Then I need my y function. So in this case, I'm going from, I need the first y coordinate to be -5. So when t is 0, I need y to be -5. And then when t is equal to 1, I want y to be 7. Okay, and then again, you could get like a slope for this thing. 7 minus -5, of course, is 12. All over 1 minus 0 is 1. And so I'll have y minus the -5. I'm just using this first ordered pair. Like in the first example there on the left, I use 0, 0 as my first ordered pair. And that will equal 12 times x minus 0. Okay, so you get y plus 5 equals 12x. And then you get y equals 12x minus 5. Well, sorry, and then we have the variable t, not x. So I'm basically using the point slope equation from pre-algebra, where it goes y minus y1 equals m times x minus x1, except I'm using different ordered pairs. Instead of x comma y, I'm using t comma x, or I'm using t comma y, right? So at the end of the day, 12t minus 5, and then you could, of course, make sure it works for these circumstances that I generated that I wanted. So when t is 0, x will be 0, and then y will be -5, and then when t is 1, x will be 2, and then y will be 12 minus 5, which is 7, and that's exactly what I wanted to happen. Okay, so you're gonna want a particular event to occur when you're creating these parametric equations for all kinds of reasons. Like what I'm saying, you want it so you have easy numbers to work with when you have to do other applications. And yeah, okay. So anyways, there's that. You could literally kind of just use this formula here as a template and then adjust it however you want and kind of get the same thing. So maybe section 3. Just let x equal, I don't know, t all over 2. And then y will equal 6 times t all over 2 minus 5, right? So this would be 3t minus 5. You can eliminate the parameter and make sure it works. So t equals 2x. And then plugging that into there, you get y equals 3 times 2x minus 5. So y is 6x minus 5. Which is, yeah, that works. Okay. And you could experiment, like I've been saying, you could experiment to see if you can kind of produce different types of orientations. So, you know, x equals maybe try negative t instead of positive t. Y would then be 6 times negative t minus 5, so the y would be negative 6t minus 5. And then you go to your t table. So in this t table, the orientation in the first kind of problem, we were 0, negative 5, and then 1, 1. We have the this orientation. So going in the kind of the standard way. Let's see if we get the same deal here. You know, what's going to happen if I put a negative in there? 0 and then 1. At 0, x is 0, and then y is negative 5. And then at 1, x is negative 1, and then y is going to be negative 6 minus 5, which is negative 11. So yeah, clearly this time you're going in the other direction, right? So the orientation is this direction. Okay. Let's look at another one, number 16. So again, I believe that in the homework you'll develop kind of your a general way of accomplishing this game. Let's say I want t to be 0 to start it at 4, 7. Okay. So how do you pull this off? Well, you kind of work with a slope and an x slope and then a y slope, right? So for your x formula, it's going to be mt plus b. So it's mt plus b, where the slope is just the difference between the two x values. So if this is x1, y1, and this is x2, y2, this slope will be x2 minus x1, and the b value is just going to be your x1. Okay. So in this case, x will be 1 minus 4, which is negative 3t, and then plus your starting position, which is at 4. Then y, the same spiel, except now you're working with y2 minus y1, and then this will be this other guy here will be your starting position, y1. Okay. So in this case, y will be y2, 1 minus 7, which is negative 6t, and then plus 7. Okay. 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 Later on, a lot of times, not a lot of times, but they'll have you do weird things like create the parametric equations for a path through the plane. For example, maybe at time t equals 0, they want you to start the origin, and then they want you to go over to this point 1, 0, and then go upwards. So maybe you're working on a box of some sort. Go all the way up to maybe 1, 3. So this would be at when t is equal to 1, and then make this t equals to 2. And then go over here and end up at 0, 3 when t is equal to 3, and then end up back at the origin at t equals 4. Okay, so yeah, it happens later in Calc 3. You need to be able to parameterize your way around a curve. So let me kind of just show you how it's done. You could probably take it for what it's worth, but so the first path is this one, and you could do the same junk that you did above, right? You could say, all right, there's an x slope, so this will be just t, and then plus your starting position. So plus 0 is just x equals t, and then y is going to be the y slope, which in this case is just 0 times t, and then plus 0, so that'll just be 0. And then make sure it works, right? So you're going from t equals 0 to t equals 1. At 0, do you get 0, 0? When t is 0, do you get 0, 0? Yes. When t is 1, do you get 1, 0? Yes. Okay, next. So I got to go from 1, 0 to 1, 3. Okay, so in this case, the x slope is 0. 1 minus 1 is 0, and then plus the starting position is 1. Then y is going to be 3 minus 0. The y slope is 3. But there's an extra issue, right? So now it's not just going from 0 to 1. It's actually starting at 1 and then going to 2. But you can kind of fake it and make it go from 0 to 1 by going not just t, but rather t minus 1. Because then when you plug in t equals 1, you'll get 0. And you plug t equals 2, you'll get 1. Okay? And then adding in the starting position, which is just 0. And then that should work, right? X equals 1, and then y equals 3t minus 3. When t is equal to 1, you get 1 comma 0. When t is equal to 2, you get 1 comma 6 minus 3 is 3, right? Okay, so carrying on then, t equals 2 to t equals 3, right? So now I have the 0.13 and I want to go to the 0.03. So in this case, the x is slope 0 minus 1, so I'm going minus t, and then plus the initial starting position, 1. And then the y equation, so there's a y slope, the 3 minus 3 is 0 times t is 0, and then plus the starting position is 3. Okay, so again, it's like you kind of see, all right, there's this formula that's happening, but we got to, that t value is going to screw it up because now I'm starting at 2, right? So instead of putting in just a t, just put in t minus 2. And then it will be like it's actually starting at 0 and then going to 1. You can make sure, like t equals 2, x will equal, I forgot my starting position of 1. So when t is 2, you'll get 1. And then when t is 2, y is always 3. And then when t is 3, you'll get x equaling negative 3 minus 2 plus 1, which is negative 1 plus 1, which is 0, which is what I want. And then y will just equal 3 again, right? All right, so your final one then, you're going from 0, 3 back to 0, 0. And again, the spiel is that you're just going x equals x2 minus x1 times t, but the t has to be adjusted now for these problems. So the t value could be t minus whatever the value of your starting position is. So I usually just put t sub 0, okay? And then plus your x1. And then the formula for y is going to be y2 minus y1 times t minus whatever your starting position is plus y1. Okay, so for this final game, I'm going from t equals 3 to t equals 4. So this is my t sub 0 is 3 in this case. So I'll have x equals x2 minus x1 is 0 times t minus 3, which is just 0, plus x1, which is 0. And then y is going to be 0 minus 3, which is minus 3, and then times t minus t0, which is 3, and then plus my y sub 1, which is 3 as well. So I'd get y equals negative 3t plus 9 plus 3. So y equals negative 3t plus 12. Check it. So when t is equal to 3, I'll get x equaling 0 automatically, and then y will equal negative 9 plus 12 is 3. And then when t equals 4, x is automatically 0. Negative 3 times 4 is 0. Sorry, negative 3 times 4 is negative 12 plus 12 is 0 for y. Okay. All right, so what I want you to do for the quiz in this section is to parameterize the following curve in the same way. So I want to go from t equals 0, I want to be at 0, 0. And then I want to end up at, let's say, 2, 0. And then I want to go up to 2, 2. And then I want to go over to 0, 2. and then finish back at 0, 0. Okay, so this should be t equals 0, t equals 1, t equals 2, t equals 3, and then you want to end at t equals 4 back at 0, 0. Okay, so what is your answer? It should be 4 equations, okay, 4 sets of parametric equations. There was my first one. Here is my second one. Here is my third one. And then here is my fourth one. Okay. Okay. So, and again, you'll be on your own in Calc 3 doing this. Okay. So that's the quiz. Let me pause the video and write it out. Okay. And a cool thing, if you really get into parameterizing curves, is this neat encyclopedia on curves. I think the book talks about the cycloid, which is an interesting curve. But anyways, all kinds of cool geometric stuff. It's in French, but if you're learning different languages, it's kind of fun to go through and take a look at it. Let's see if they have. So they have really unusual ones, like that are made from, I don't know, like if you're a BMX rider, a bicycle rider, or a skateboarder, and you're doing these weird kind of patterns. They have some of those in there. Let's just kind of look at a couple of them. I think the interesting thing would be trying to code these into a computer of some sort. Note that a lot of these, they may look kind of boring if you're just looking at them, but you can animate a lot of them. Like this guy, the curve generated by this sort of vehicle going on. Curve suivant. See if oh, look at this guy. So you're taking a wheel that maybe you can imagine has a little pen attached to it, and you're letting the wheel move around the circle. Back in the day, way back before they knew the orbits of the planets were, before they knew that the planets were going around the sun and not vice versa, they had these really, really elaborate curves to talk about why the planets were doing what they did. So if you looked out in the sky and maybe you saw Mars, at some point Mars looks to be going backwards, okay, having some, maybe they call it retrograde motion or something like that. Anyways, they got really good at predicting the locations of the planets using these cycloids, epicycloids, and things like that. They were very accurate. It's just that everything became extremely simplified once they realized, hey, the Earth is not the center of the solar system, and moved on. Then all the formulas just became super easy to deal with. But we still have all of this kind of math that probably came from that study, and it's all very, very interesting. And I encourage you to go online and find something about math you like, right? It's hard doing something that you don't enjoy, that you have no interest in doing. Find something, please, about math before it's too late. If you get into a job you hate or something like that. But this stuff's really cool. You go through and take a look-see. All right. The last topic I kind of have to deal with is this idea of smoothness of curves. So because we have the separation between the two formulas, you can have a derivative of the x portion that's kind of equal to 0. That would cause like a division by 0 scenario if you were trying to find the derivative back in Calc 1. Okay, whenever that limit didn't exist. So if you had a situation where you're approaching a limit and you pretty much are dealing with a 0 in the denominator case, it's going to go off to infinity. Fortunately, in parametric equationville, you can deal with those issues, but we do kind of note that the objects are not going to be smooth in cases where both the derivatives are simultaneously equal to 0. So anyways, we'll worry more about the calculus of parametric equations in the next section. But they make a note of it here when they introduce the cycloid. Anyways, a curve is smooth when f prime and g prime are both continuous and not simultaneously equal to 0. From the graph, you can usually tell where the picture is not smooth, and it'll be where you have those kinks in the graph. So I think we probably saw one here. Of course, it's the one with the little truck, and you see these huge kinks on the graph. Jeez, how many graphs did I look at, you know? And this one, this epicycloid here, you can see the kinks when the red curve goes down right there. When it hits that blue curve and you have that kink, that's where it's not considered smooth, okay? Let's see if this one has any kinks in it. Doesn't really seem to have any kinks. Oops. This one has them all, the epicycloid does. But this one especially, you see those corners, like if you fell from the sky and you landed on one of those, you'd be dead. Those things, that's where it's not smooth. Okay. All right, so let's look at number 17 and kind of try to find where the parametric curve is not going to be smooth. And in this case, it's going to turn into kind of a trigonometry problem. And I believe if you were to graph this, it would be a cycloid. Okay. But anyways, you need the derivatives. And you just take the derivative here with respect to x. So if I were to write it out in more of the Leibniz derivative notation, dx with respect to theta. Okay. So the derivative of 3 theta would be 3, and then minus 3 cosine theta. And then the derivative of y with respect to theta, the derivative of 3 is 0, the derivative of cosine is negative sine, so negative negative is positive, 3 cosine theta, or sine theta. Okay. And then these both are continuous everywhere, so I ain't got that issue. It's the simultaneously equal to 0 issue I need to watch out for. So what I do is set each one of these equal to 0 and see if I could get a theta value where they're both simultaneously equal to 0. Okay? So here I am just finding where 1 is equal to 0. So I'm looking for where cosine theta is equal to, what did I screw up the signs there? So it should be positive 3. So where is cosine theta just equal to positive 1? And of course, that would be where theta equals, well, 0 plus 2 pi n. So infinite solutions there. And then on the other case, I'm taking 3 sine. I don't know why I have a double theta there. 3 sine of theta set it equal to 0. Solve for sine theta. And then think about the unit circle. So sine, oh, I screwed up that. No, you're good. You're good. So in this case, it's pi n, right? Because sine is going to be equal to 0 here and here, whereas cosine was equal to 1 only at this location, and then any 360 degrees rotation from that location. But sine it goes back and forth. Cosine of pi is equal to negative 1. That's why you don't include that other side there. But this will be then 0 plus just pi n. And so the simultaneous case then is when it's the 0 plus 2 pi n. Right? So that implies it's non-smooth at theta equals 0 plus 2 pi n. Okay? Or just 2 pi n. All right, so that'll do it in this video. As usual, thank you for watching. I'll see you next time.